The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Any questions about the sorting methods that you want me to go over in depth while I revise? Okay. All right, sorting.
Oh, lectures are pretty good. So.
What sorting methods have we learned? Let's start from dumbest to smartest.
Merge sort?
Okay, somewhere in the middle. Merge sort isn't very bad. What's the easiest method to sort?
Insertion.
Insertion sort. Excellent. All right, what else? Heap sort. And I gave 2 away now.
Counting?
Counting sort, very good. And oh wow, if we don't even have the name of it. So the last one is Radix sort. What are the running times for these 3 that you guys remember?
Insertion sort is linear, I believe, or more.
I want to see your pseudocode for insertion sort.
That's really bad.
So linear is as good as you could possibly get. So sorting takes an array of random stuff and outputs an array of things in a sorted order. The array is size n, so it has to output an array of size n. If you can do an algorithm that runs in order n time, then that's the best you could possibly accomplish, because you have to output n elements. So the best possible time you could get for sorting is theta of n. All right, how about merge sort? Thank you. Heap sort.
Order H, which is log n, I believe.
Order h where h is log n, OK. And you're missing a factor. So a heap operation takes order h, which is log n. So if I have to insert a number in a heap or extract a number from a heap, that's log n. In order to sort an array, how many insertions do I do?
I think, I don't know.
OK, wild guess?
N.
Very good. See, there you go. So you need to insert all your numbers in a heap and then extract them one by one. And you will get them in the correct order that gives you the sorted result. So n log n. Does anyone remember what's special about these 3 sorting methods that does not apply to the other 2?
They're in place.
Merge sort isn't quite in place. If it would be in place, it would be perfect. There is actually a way of making in place merge sort, but it requires a PhD degree to understand that. So we will not cover it in 6006 because I do not understand it, so I couldn't explain it. So merge sort is not quite in place. Which one is in place?
Heap sort.
Good. So heap sort is in place, merge sort is not in place, and insertion sort, it's really slow, so we don't care that much about it. So what's special about these 3 that does not apply to these 2?
You don't have to use integers.
OK, you don't have to use integers. What do they want to know instead about the things you use? So we'll call them keys.
You need to be able to compare them.
All right.
But you don't need to have a minimum and a maximum integer.
So it turns out if you have a comparison operator, you will have a minimum and a maximum. But that's complex abstract algebra that we don't need to worry about. So you gave me the good answer, which is they use something called a comparison model. And in that model, you do not need to know too much about your keys, so the elements in the array that you're sorting. Your keys are blobs, and all they have to be able to do is know, if you have 2 of them, you have to know which one's greater. That's it, nothing else. What's the problem with the comparison model?
It takes time to compare things. That's like with everything.
Yeah. So we learned in lecture that there is a lower bound for the comparison model. And if you want to sort using nothing but this information, that will take you at least n log n time. You cannot do better than n log n if all you're using is comparisons. So in that respect, merge sort and heap sort are optimal. If you want to stay within this model, this is the best time you're going to get. Does anyone know how you can implement this comparison model in Python? So numbers respond to these operators, right? Actually, in Python, this is equals equals. What if I have a random object and I want to make it respond to these operators? So for example, I write merge sort. We wrote merge sort. And now I have my own objects, my own keys, which are not necessarily integers, because that's why we like this. And we want to make them respond to these operators so that I can call merge sort on an array of them and it wouldn't crash. What do I have to do?
I mean, you have to give the keys values if you compare.
So suppose this is my key class.
Isn't there like the LT and GT and like
All right, there are some magical methods in Python. So there is the old school model, which you might see in legacy code, which only works in Python 2x, which is you define a method called CMP that takes self and other. And it has to return a number that's either smaller than 0, equal to 0, or greater than 0. And this maps to this. So you'll see this in old code, but you shouldn't use it in new code unless you have a very good reason to. Instead, the new model says that you define special methods called LT, which stands for less than. So it's this guy. LE, which is less or equal. GT, which is greater than. And GE, which is greater or equal. And if you look at our code for psets 2 and 3, we have some objects that pretend they're keys. And we have to define these methods. Also, when you define these, it's a good idea to define EQ for equality comparison and NE, which is this guy. So these also take self and the other key that you're comparing with, and they return true false. So this will help you understand the code better. All right, so with relatively little work, you can have any wild object you want act as a key. And then you have insertion sort, merge sort, heap sort, heaps, binary trees, AVLs, everything works because everything uses the comparison model. The problem is this n log n bound. It's not as fast as the best possible sorting algorithm you could come up with. Right? This is slower than this. So that's why we have to break out of the comparison model, and we have to look into these boxes and get more information so that we can write faster sorting algorithms. Does anyone remember the running time for counting sort? OK.
N plus K.
OK. Let's remember how counting sort looks like. Let's get this array that there should be enough. 4, 1, 3, 2, 3. How do we sort it using counting sort?
We initialize an array of all of the possible
Very good, very good. So counting sort needs to know something about your values, right? It makes an assumption. And the assumption is that these values are integers from 0 to, say, k minus 1. So you have k possible values. And they don't really have to be these as long as you can map them to these numbers. So we are going to initialize an array. Let's say this is an array, and 0, 1. So 0, 1, 2, 3, 4, 5. So we're going to initialize it with,
zeros.
all right. And then?
Iterate over our list to sort,
OK.
incrementing the corresponding value to each key in your.
So which one am I incrementing here?
Pardon?
Which one am I incrementing here?
The 0 underneath your pair.
OK.
1.
OK. 3, 2, and then?
3 again.
So this becomes a 2. And what do I do now?
Reiterate over that. I don't know what to call that.
Array.
Dictionary almost. Okay, an array.
OK.
Printing into your output array 1, 1, 1, 2, 2 3s, 1 4.
All right. So there's no zeros and no fives. So 1, 1, 1, 2, 1, 3, and 1, 4. OK, so far so good. This is great. There's one thing that's missing. For counting sort and for other sorting algorithms, we care about the property called stability. And stability means that if you have 2 equal keys, or at least 2 keys that look equal to the sorting algorithm, they might be different objects because they might be implementing that. The one that shows up first in the input should also show up first in the output. And that requires particular care because you can't just look at the keys from your sorting perspective and know which one's supposed to go where. You have to remember where they were in the input. So if this guy is 3A and this guy is 3B, I can't use this approach anymore, right? Because when I'm outputting here, all I know is I have to output a 3. I don't have any other information associated with the key. So instead, I have to do something smarter.
Either replace your array with a 2D array, or I think better would be to replace each value with a linked list.
OK, so we can replace each value with a linked list, which would have the keys that map to it, right? So here I would have a 1, here I would have a 2, here I would have 3A and then 3B, and here I would have a 4, right? So then I can go through these and output them the right way. OK, now suppose I'm writing this in C. Suppose I'm in a low-level language, and I'm in a low-level language because I'm hired by one of these startups that are doing NoSQL databases, and they're writing everything in C to make their things really fast. So I'm writing an index that uses counting sort. I don't have linked lists because if I'm writing in C, I have to write my own, and that's hard. So I want to implement this in another way. Linked lists are hard. What would I do instead? Can anyone think of another way?
I think you can like decrement values in the C, like in the array that you have where you have kept the counter of each element.
OK, so you have the right idea. You're missing one step. So I'll give everyone else a hint so that everyone can catch up. So what I want to do is I want to take this and transform it into something that allows me to go through the keys. So I know I have 5 keys here. I'm going to make an output array of 5 elements. And I want to be able to see 4 and know that it belongs here. C1, know that it belongs here. C3a, know that it belongs here. Then probably update the value associated with 3. C2, know that it belongs here. And then when I see 3b, know that it belongs here. So I want to look, when I get to 3a, I want to look inside here. And I want this to tell me that 3 belongs here. 3a belongs here. So what would the position of 3a be? That's not good, right? Let's call this C instead so that I can say 3AB. So how would I define the position using the sorted property? So 3A should go in the index that is how many keys smaller than 3 there are. So if I can look through here and see how many keys do I have that are smaller than 3, this is where 3A needs to go, right? If I look at 4, there are 4 keys that are smaller than 4, so it needs to go in position 4.
Well, that almost seems more like a compare. I guess that means it is kind of a comparison model, but like you're just saying, is it greater than? So it's not really counting sort anymore as much.
Well, I'm telling you I can compute that using this. So I can use the counting sort algorithm and change this array a little bit so that I can do this trick and know what goes where.
Well, he already mentioned using a 2D array,
but a 2D array would be too much. I want to, in the end, I will be changing this in place, so no extra space except for this array of size k. But let's not worry about changing it in place right now. Let's say we're going to make another array of size k. And I want to compute. So I want it to tell me that, I guess I don't care about this, but I want it to tell me that the first one should go here, the first 2 should go here, the first 3 should go here, the first 4 should go here. How do I do that?
I mean, you could make that array, right?
But how do I compute it?
While you're making this one, you could start filling that one in. While you're making the top one.
Can I?
Oh, it would be like insert and sort though, kind of, because so you come across the 4, you put it in there because you know how many there are, but that doesn't make a lot of sense.
Yeah. Okay.
Yeah.
So let's abandon that road. Let's think of something else.
Could you populate the array with the number of elements that are less than that?
Yep.
position?
So intuitively, I want this to tell me how many elements there are smaller than 2. This should tell me the number of elements that are smaller than 3, so on and so forth. OK, how would I compute that?
So
Let's see what it's supposed to be. Let's fill it out with real values. 0. How many elements smaller than 1?
0.
How many elements smaller than 2? How many elements smaller than 3?
It's a cumulative sum
OK.
on the array above.
So this is how many elements smaller than 4? 4. How many elements smaller than 5? 4. OK. What's the difference between these two guys?
1,
What's the difference between these two guys?
1,
Yeah, you're right. Sorry. Thank you. What's the difference between these two guys?
2, 1.
And what's the difference between these two guys?
0.
OK, what did I just write here?
Same series up there.
Right.
All right. So this guy is 0, right? Because there's no element there's nothing that's smaller to the smallest key. And then this guy is whatever was here plus this. Well, almost. So the difference between this guy and this guy is this.
So why array? Why did you bother? Why did we make a new array? Because we can just get that information.
I'm making a new array so that we can see how to compute it. So now we're going to try to write pseudocode that does this in place. So suppose this array is A, and this array is pause for position. And suppose, sorry, not this array. This array is A. This array is pause, and I start with this, and I want to end up with this. So let's try to write the pseudocode for counting sort. Counting sort with an array A. I'm not going to write the first 2 lines that produce this. Let's transform this to this. How would I do that?
Initialize an array of the same size.
Okay. Can we try to do it in place?
Sure.
Okay, how do we do it in place?
Or
You could, well, you know, for 4, you feel like you get the 4, you're like, oh, I haven't encountered anything below me, so you put in a 0 initially for 4. And then you get a 1, you're like, oh, I haven't gotten anything below me, but you have to keep track of the fact that, so you have to iterate over the list every single time you get a new input.
So I don't want to do that because that's n
I think
squared.
what you need to do is keep a running sum.
Okay.
Is it a register? Is that what you're calling it?
Running sum, I like running sum.
Okay, keep a running sum of
Sums always start at 0, right?
right.
Okay.
So you keep 0. You take the value in each index of that array and add it to sum.
Okay. So for I iterating from 0 to, so you want each value in this array, right?
Yes.
So it's going to iterate from 0 to what? How many elements do I have there?
10. Like, okay.
Okay, almost. So we're using Python numbering, which is zero-based indexing. The indices look like this. So it's 0 to, very good, thank you. And you said I'm going to add the elements to the sum. So sum is sum plus position of I. Okay. And then?
The replace is the hard step. Right? So 0 should be 0 still. 1 should be the sum after evaluating 0. You'll need a temp variable.
Okay.
You'll need to grab position I and put it in temp.
Temp is position I.
Then say position I is sum before incrementing sum. No, that's not going to work.
Really?
You have to say then sum is sum plus temp.
Okay.
That is going to work. Probably.
Okay, how does everyone else feel about this? Does it make sense?
Not really.
Now, your temp variable has to be the one from the previous iteration because, right, so when you first start it, it's the very initial case that doesn't work. So like if you're in the first column, everything's fine, then you go to column 1, you're looking at everything to the left of it, it's still going to be 0. Then you go to the second column, but you already overwrote the previous column. So you need to store somehow the, I don't know, it's just the initial case from when it first like goes from 0 to like an actual quantified number. Because otherwise you're just going to get like 0, 0, 0 because you're just overwriting.
Can you store temp at the end of the loop? And use it before you change?
Okay. Sorry, I'm getting confused. Okay, this is getting hard, so I will show you a trick to make life easier. I'm going to put, how many elements do I have here? 5, right? So I'm going to put a 5 here after the array, and then I'm going to ask you what's this difference? Okay. So now we have this whole array. Okay. Can people see what's going on here? So instead of starting at the beginning, I'm going to start at the end, and I'm going to know, I know for sure there are n elements. Therefore, the index of this guy is n minus, so the index of the last key is n minus how many keys I have with this value. Does this make sense?
Right, but you're iterating over it in order, right? So we can't just take the whole thing and say we're going to shift it over to the right one.
How about,
So like as you're going to left to right, you only know what you've seen thus far.
how about going it for ai from n minus 1 to 0? Would it work then? So what would I write?
But isn't that super inefficient? Because then you're starting looking at the whole list, and then you're sort of, rather than just looking at the previous sum that you just accumulated.
So-
So your first iteration, you have to add up everything that you see. Second iteration, you have to add everything up.
Okay, so if I add everything up here, what's the result going to be?
5.
Okay, what's 5? So this counts how many 0 keys I've seen, how many 1 keys I've seen, how many 2 keys I've seen, so on and so forth. So in
you're
total,
just subtracting,
it's
like,
how many keys I've seen, right? All this, the sum of all these is how many keys I've seen.
yeah.
How many keys do I have?
5.
Okay.
So like for each one you see, you just.
So who's 5? It's the length of this guy, right?
Yeah.
And we usually call that n. So when we're doing sorting, this is n. So maybe it's less confusing. Oh, I already used n in 2 places, so I guess that's it. I could say the length of a, but there you go. So I could do the thing that we're going through before. I could figure out my temp variables and I could make it work.
I think it's
Or I could do this.
I think it's the same though, isn't it?
Yep.
Okay.
It's the same thing, except I think this is easier to write. Does anyone want to help me write this?
Maybe doing, once you're starting with the top array and then finding the bottom one?
Yeah.
Oh, okay, well you start with the first one and the one ahead of it. And, I mean, starting from the top array, sorry.
Okay, so I have this.
Mm-hmm.
And then what do I do?
From n minus 1 to 0. Oh, so you're still starting from the back.
Yep.
Well, then you just compare that to, I mean, you're going to start with a 0 difference if you have, well, you don't have any of those last keys, so you have to start with a 0.
So what's the difference between 5 here, which is n, and this guy? What is this?
It's going to be 0.
But what is it? Why is it 0? So this one's 0, this one's 1, this one's 2. What is this? It's the last guy here, right?
Yeah, yeah.
So this is pos of n minus 1.
Yeah.
This is pos of n minus 2, so on and so forth.
Mm-hmm.
So to get from n to the value here, I have to subtract this guy. So
Pos of I, right?
pos of I.
Well, it length of A,
Equals
right?
sum minus pos of
Okay, very good.
and then update sum. Sum equals pos I.
Sweet. No temp variables aside from this, I guess. How does this look like? Do people get it?
You're subtracting pos of I, or you're subtracting a of
It's all one array.
I? It's the same thing, that's right. That's
So
right. Okay.
A is this array. A is the input array.
I get it.
And pos is this guy. And this is pos before the for loop, and this is pos after the for loop.
I get it.
So I guess this is pos 0, and this is pos 1. And here we start with pos 0. This we end up with pos 1. OK. So we're able to compute this. There are many ways of doing this, but in the end you want an array that looks like that. Right? This is counting sort. This is the hard part of counting sort, coming up with that array. Once you come up with that array, you're golden. So let's see that we're golden and produce an output array with the keys in the right order. So say we have an array called output, and this is going to have these keys in the right order. What's the pseudocode for that? First, I'm going to create a new array, and I'm going to initialize it with n nil values. Then what do I do?
Iterate over A.
Very good. For, nah, it's too low. Let's do it here.
For I in A.
For from 0 to n minus 1. Okay. What do I do?
Out of, no, it has to be, ooh, can we modify pos 1 as we go?
Yep.
So you could say out of pos 1.
So by the way, this is pos. The reason I labeled them with 0 and 1, so we're doing the change in place.
Right.
The reason I labeled them is to say that this is what pos is before we're going into the loop. This is what pos is afterwards. But it's a single array. So let's call it pos. So out of pos of
I
yep.
equals A of I.
Okay.
Pos of I plus pos. Or, yeah.
Yep. And I'm going to use the CLRS way, which makes me write more. Okay. So how would this work? I have this array here. I start at 4. What's pos of 4?
4.
All right, so I'm going to write this at position 4. I should probably make this a proper array. 1, 2, 3, 4, 5. So at 4, I write 4. And then I increment this guy to become 5. Then I get 1. So I look at pos of
1.
OK. And that is 0. So I'm going to write 1 at position 0. And I'm going to increment it. Then I get to 3a. I look at pos of 3. It says 2. So I'm going to write 3a here and increment this. Then I get to 2. Pos of 2 is 1. So I write 2 here. Pos of 2 becomes 2. Then I have 3c, which is pos of 3 is now 3. It's not 2 anymore. So yay, I'm not overriding 3a. That's good. And this becomes 4. OK, are people getting what just happened here?
Wait, why did? Oh, I guess so you're just basically turning the next array into an index binder.
Yep. So this guy tells me if I have a key, where do I write it in here? So these start out with pointers to the first element that would store that key value. And when I store a key, say when I store 3a, when I get to 3c, I don't want to store it in the same place. So I have to increment that. I have to say, yo, I wrote 3a at position 2. So next time, next time you see a 3, write it at the position following that. And that's what this guy does. OK, so this is the relatively easy part. And this is the hard magic in counting sort. So how are people feeling about it now? Any nods, or is it still confusing as hell?
Not unconfusing.
OK. Well, what should we do? Do you guys want to ask more questions? Do you want to run through another example? Do you want to try to see how this becomes useful in Radix sort so that you're motivated to figure it out on your own. What would make more sense? All right, who wants to do more count sort? Who wants to do some Radix sort? All right, Radix sort it is. Next time you want to move on, tell me you understood, and I'll believe you, and it'll look good on tape. 2, 3,
Just to tell us that there's a camera here.
1, 4. I think you're supposed to know, because otherwise you don't know that we're violating your rights. 2, 4, 1,
There's a
3.
sign on the door.
1, 2, 4, 3. 2, 1, 4, 3. So, oh, and one more. 1, 2, 3, 4. So this is to refresh your memory. What do keys look like in merge in Radix sort? So in count sort, the keys have to be numbers from 0 to k minus 1. How about merge sort? What do keys look like? So Radix sort says that a key is a sequence of digits. Say you have d digits in a key, but then each digit isn't necessarily a base 10 digit like we're used to. Each digit is in base k. So each digit can be from 0 to k minus 1, and we're using base k. How many keys can I represent this way? So if you have numbers of n digits in base k, what's the biggest number that we can represent? Or how many numbers can we represent with that?
N to the k. No, d to the k. Right?
Almost.
K to the D.
All right, so if our base is 2, like if we're using bits, then our base is 2. And if I have 8 bits, then 2 to the 8. Cool. So if I add one more digit, I get to multiply the number of keys I represent by k. How do I Radix sort? Does anyone remember?
You take the log base K of everything? I guess no, log base D of everything. K, base
No. No, that would be hard math. We don't do hard math.
Okay.
In sorting, if you have integers going into your sort, you only do integer operations. You don't do anything mathy on them. So what we do is we've broken up the keys into d digits for a reason. We're going to have d rounds in the sort. And in each round, we're going to take all the keys that we have, and we're going to sort them according to one of the digits. So in one round, we'll sort them according to this digit. In one round, we'll sort them according to this digit, this digit, this digit. Which digit do we start with? What do you guys think?
It's the least significant bit, right?
The most significant on the left.
OK. So this or this?
Right side.
100 is bigger than 1, even though the 1 is bigger than the 0 in 100.
OK. You're helping me out. So the point I'm trying to make here is Radix sort is unintuitive. If we ask you on a quiz, what do you start with? Your intuition will tell you to start with the most significant digit. Go against it. In Radix sort, you start with the least significant digit and then move your way up. So Radix sort goes like this.
I mean, it does make sense because you don't have very much information at the most significant bit. So, I mean, you could get a bunch of 2s, but that doesn't give you that much information. The most information is the smallest bit, and then you move up from there.
It depends what information you're trying to get. But maybe you know the algorithm, so you're thinking, oh, by knowing the algorithm, I know that I'll have the most information by looking at it this way. All right, so let's sort these by the last digit.
Done.
Sweet. Let's sort them by the digit before the last digit. What do I have to do in my sorting? What do I have to pay attention to? So the sorting method that I use has to have a property. It can't be any kind of sorting. Stable. So the reason we went through all this pain in counting sort is because we want to have a stable sort here. Now let's try to sort these in a stable manner. This is the first one, 2, 4, 1, 3. Then I have 2 3s, so 1, 4, 3, 2, 1, 2, 3, 4. And then I have 3 4s. 2, 3, 4, 1, 2, 4, 1, 3, 2, 1, 4, 3. Wait, this isn't good. 2, 3, 4, 1, 1, 2, 4, 3.
Should cross them off if you write them down.
I should. I was hoping you guys will help me if I mess up. Okay, so now these are sorted stably. Let's look at these last 3 that have the same digit here. So they have the same 4. If you look at the last digit, because I used a stable sorting, they're also sorted according to this last digit. So they're sorted according to these last 2 digits, because the sorting that I used is stable. So now if I sort according to this digit, then if my sorting is stable, they're going to be sorted according to the last 3 digits. So as I go from my last digit to my first digit, the keys are going to be sorted according to the last digit, last 2 digits, last 3 digits, and then all the way up to everything. This is why I need a stable sort, and also this is why I need to start from the end. Okay, does this make some sense? What stable sort did we just learn? Counting sort. All right, so we're going to use counting sort for this. What's the running time for one round? So for one sorting. One counting sort takes how much time?
This is a Radix sort.
Yeah, so Radix sort is d rounds of counting sort, right? Count sort this, count sort this, count sort this, count sort this. So one round, one counting sort. What's the running time? Thank you. Now how about d of these? What's the running time? Okay, but I want to come back here, and I want to be able to say that Radix sort is optimal. I want to be able to say that it is order n. So what do I have to do in order to be able to say that? Okay, so you're going from, you know the answer. You're going from the fact that you know the answer. Okay, very good. What if we wouldn't know the answer? What do I need to do?
Well, we know the first part is order n, so
So d has to be,
we want dn to be greater than dk, right?
well, so dn has to be at most O of n, right?
Yeah.
Because otherwise the whole thing would go above, so that wouldn't work. So then what can I say about d?
Constant.
Very good. And how do you write constants in math mode?
Order 1.
Very good. So d has to be order 1. Otherwise, it's not going to come out to that. Now, what else do we know? We have this, that's order n plus k. If I set this to be a lot smaller than k, if I set it to be log n, it's going to be order n. If I set it k to be a constant, if I use bits, if I use base 2, so I set k equal 2, this is still going to be order n. So if k goes way below n, this step is still going to be order n. So I might as well set k as high as possible. So k is order n, because that's the highest thing I could set it to. Now, why do I want to do that? Yes?
What
You have a
does
question?
k physically represent in counting sort again? The length of what?
So in counting sort, n is your input, how many keys you have, and k is the size of this array.
Oh, okay.
So you have to be able to map your keys from
So
0
k
to
is
k minus
set
1.
by n, basically, right? Or well, no, it's set by the elements.
Yeah, it's set by the nature of the keys.
Okay, yeah.
So in real life, we're thinking maybe we have some huge numbers that we want to sort. And we're going to chunk them up into, when we're writing on the board, we always have to chunk them up in base 10 digits because that's the only way we know how to write. But in a computer memory, you can chunk them up into, say, base 10,000 digits. And the fewer digits you have, the faster this is going to run. So we have to figure out what's the base. And it turns out that if you want to have radix sort run in order and time, well, the number of digits has to be sort of constant. I know that k should be order n because I have no interest in making it lower than that. So these two bounds together tell me that the keys that I can sort are from 0 up to order n of order 1. And this looks terrible, but what it comes up to is that you can sort keys that look like n to some constant for any constant. So you can sort huge keys as long as huge still means finite. And as long as you can figure out how to map them to numbers. Does this make some sense? OK, would we ever want to use merge sort instead of counting sort? Suppose we had a stable merge sort. Would we want to use that? Instead of counting sort here. What would happen? So suppose it's stable, so it's correct. The algorithm isn't going to blow up. What's the running time for a merge sort? So if I use a merge sort. So if I use d merge sorts, it's going to be d times n log n. So no matter how small d is, I'm still not running in linear time. So merge sort does not go well with radix sort. OK, so from my end, we're pretty much done. We started with n log n, and we got to a sorting algorithm that's order n. We started at the beginning of the recitation saying that the best thing we can do is omega. Is that omega? Yeah, omega of n. We got to that limit. We're happy. We're going to be done with sorting. Any questions from you guys? That means everyone's confused, right? Yes, thank you.
Can you explain what the stability criterion is again?
The
stability for these sorting algorithms. Which ones are stable and what makes it unstable?
All right, very good. Thank you. So I like especially the last part with which ones are stable. I'd like to go through that. So a stable sorting algorithm means that if you have two keys that are equal, the key that shows up first in the input is the key that is produced to the output. So in this model, your keys are not necessarily integers. Your keys might be those weird classes that implement some method that maps them to integers. So say there's a method there, underscore, underscore, int, underscore, underscore, that gives you the integer for that. So the sorting algorithm would only see a 3 here. But in fact, this is a complex object. And this is another complex object, but the sorting only sees the 3. If this guy shows up before this guy in the input, they have to show up in the same order in the output.
Why would that be bad if they're switched?
It's not stable. So if they're switched, then when we're using a stable sorting algorithm here. So here the key is this complicated object, right? But say we're in the second round. We're in this round which we played with. Even though the key is this whole complicated object, the only thing that the counting sort sees is this number. So this guy looks like 3. This guy looks like 3. And these 3 guys, although they're different, they look like 4. If I don't output them in the right order, if, say, I output this one all the way at the end, then I'm going to get 2, 3, 4, 1 to be down here. And now my numbers aren't sorted by the last 2 digits anymore. So it breaks any algorithm that assumes stability. So stability is something that you get from a sort because it's convenient to assume it in some other algorithm that builds up on that sort. If you don't need it, you don't care about it. But in some cases, you need it. And for the second part, which algorithms are stable? Is insertion sort stable?
Assume so. I mean, stable mean correct, right?
No. We mean that property there.
They'll be, oh, I see, you mean in order.
Yep.
Okay. Well, insertion sort goes in order, but I guess you could push other things out of order.
So in insertion sort, you're doing swapping to move things to the left. But if you find two things that are equal, you're never going to swap them.
Okay.
So insertion sort is in order, is stable. Merge sort, the one we gave you in docdist is not stable, but there is a one character change that makes it stable. And you should look at today's lecture notes to find out what that is. So merge sort can be stable. Heap sort, stable or unstable? Unstable, and there's a really small example that you should look at. Counting sort, stable or unstable? Thank you. It would have broken my heart if this would have come out wrong. And radix sort?
Yes.
Probably stable, right? All right. Any more questions? I like that question, by the way, because you made me do this. I liked it. Any more questions? All right, then thank you, guys.